ML. And yeah, so we are even more curious on your keynote. But before that, I would like to formally introduce you. And yeah, I have my biography or your biography in front of me. And yeah, you are currently a research scientist manager at Meta. By the way, our website says Facebook, so we're a little bit outdated. Your research sits at the intersection of computer architecture, machine learning, with emphasis on developing energy and memory efficient systems and microarchitectures, optimizing systems for machine learning execution at scale, and designing learning-based approaches for system design and operation. You are passionate about pathfinding and tackling system challenges to enable efficient, responsible AI execution. You chair the MLPerf recommendation benchmark advisory board. You co-chaired the inference and serve on the ML Commons board as director. Prior to Meta, you was tenured associate professor at ASU, and yeah, you hold a lot of other chairing positions, for example, for the Conference on Machine Learning and Systems in 22, and you're program chair of, or have been program chair of the 2018 IEEE International Symposium on Workload Characterization. You received numerous awards, among which the NSF Career Award, Distinction of Honorable Mention of the CRA Anita Borg Early Career Award, and many, many more. I'm not going to read them out aloud now, because that would actually take a lot of time away from that keynote that you're now about to give. It's on sustainable AI. And as I mentioned, we're really curious. We had a lot of spoilers and yesterday already. So without further ado, Carole, welcome to eEnergy. Thank you for being willing to give a keynote presentation, and the floor is yours.
Cool. Thanks so much for the kind introduction, Sebastian, and thanks so much for having me here at the eEnergy conference. Can you see my slide deck? Cool. Hi, everyone. It's a great honor to be here. My name is Carole, and I'm currently doing research at Meta AI. I'm a computer architect by training, where my research is focused on improving the execution efficiencies of computer systems in general. One of my latest work lies in developing and advocating for responsible innovations for computing technologies. And so today I would like to take this opportunity to share with you some of my thoughts on how to scale AI sustainably in an environmentally sustainable way. So if we take a look at the evolution of AI has been driving an unprecedented growth in the overall computing industry in the past decade. This is the tremendous use case demand, and that has energized this ever-increasing investments into artificial intelligence, which in turn has stimulated novel applications in many different domains, such as science. We start to see AI in medicine, finance, education, and entertainment as well. AI, for example, has been used to discover new electrocatalysts for more efficient and scalable ways to store and utilize renewable energy. AI has also been applied to predict the protein structures that has the potential to revolutionize the biological science domain. AI is increasingly used by the agriculture industries to grow plants using much less natural resources. Yesterday, Professor Vijay Reddy's keynote talked about how we can use technologies to improve also energies in residential buildings and in smart city settings as well. Oh, at the same time, AI is also used to tackle climate challenges. Enterprise AI is already a $1 trillion market, and it is projected that the market of AI will continue to increase exponentially for the next decade. If we take a look at what is driving this AI revolution, it is fueled by decades of innovation by the computing hardware industry. Today, modern microprocessors come with over millions times more transistors as compared to the very first one from 50 years ago. Modern processors now run more than 750 times faster as compared to the first Intel 44. And the strong demand on computational performance really requires system architectures to scale up performance beyond single node system. So for example, for AI, Meta is building world-class superclusters by horizontally scaling out the computing infrastructures to tens of thousands of bleeding-edge GPUs. We are also seeing a large portfolio of domain-specific accelerators on the market, aiming to achieve high performance and high energy efficiency for AI and many other key algorithms on the horizon. So this decades of technological innovations have made computing many orders of magnitude more efficient through vertical scaling, through horizontal scaling, and through tons of hardware specialization innovations. And with each generation of accelerators, we expect to see the machine learning clusters to become increasingly more heterogeneous, which is opening up a lot of optimization opportunities for software and resource management. The significant efficiency improvements is also stimulating novel applications at an ever faster pace. Now, if we look at the overall energy consumption of the entire computing industry, it is quite significant. Overall, the ICT industry produced over 700 million tons of carbon dioxide, and that includes the energy footprints of consumer electronics at the edge, the networking and communication fabrics, and the large-scale data centers. The overall carbon emission is about half of the entire aviation industry. Now, a significant part of computing's emission comes from hyperscale data centers. So if we take a look at the energy footprints of large technology companies like Microsoft, Google, and Meta, we continue to see the energy footprint to increase rapidly over the past 5 years. So going forward, there are many reasons why we also expect this energy consumption to increase in the next decade. First, only half of the world population is connected on the internet. For United States, about 25% of the population still don't have home broadband connections. As more people are connected to the internet, we expect the usage and energy footprints to increase as well. Second, there are many new emerging use cases, novel applications coming online. AI is being one of the most significant driver, but there are many others that we must also pay attention to. And finally, Moore's law scaling has really slowed down. Hyperscale data centers today has been quite optimized in terms of power usage effectiveness. And so it will be increasingly more challenging to further improve computing's performance efficiency. It is projected that the overall energy consumption of the overall computing industry will reach 7% of the global energy demand by 2030. So this large energy footprint has significant environmental implications. Now, recognizing the significant environmental implications of computing, what technology companies are doing is already making various climate pledges. For example, Facebook, Meta, Microsoft, Google have all reached net zero for its operational energy consumption at the overall company level, and that includes data centers, power consumption, as well as office buildings and many others. And one of the common approach to reach this net zero is to neutralize operational electricity usage by procuring sufficient renewable energy in order to offset that majority of carbon emissions produced during the use phase. For example, Meta has renewable energy contract for more than 6 gigawatts of wind and solar energy generation across 18 states and over 5 countries. In many cases, this renewable energy project are located on exactly the same power grid where Meta's data center are located. However, renewable energy can be challenging to use because of the intermittent nature of these renewable energy generation. And for example, in many states, renewable energy generation can often be curtailed because the electricity demand is really hard to predict and to match the demand. So there is this demand response challenge for renewable energy usage. Another quite interesting data point is that in 2020, renewable energy sources accounted for about 12% of the total US energy consumption, despite the fact that it is about 20% of the overall electricity generation. This tells us a little bit about how this renewable energy utilization can be quite challenging to fully utilize all the renewable generations that we have. Finally, while renewable energy production is growing, this renewable energy infrastructure is going to take some time to build and fully reach all the energy consumption globally. So we cannot solely rely on renewable energy to solve computing's environmental footprint challenge. In fact, there's a lot more we as a technology developer, researchers, and engineers can do to help us maximize the renewable energy utilization. So what are some of the interesting opportunities for us to tackle? AI, artificial intelligence, being one of the fastest growing driver for the entire computing industry in the past decade, is going to be focus of my talk today. So first, we are going to take a look at the scaling trend of modern AI workloads. And then we'll go over the overall AI model development cycle. We are going to take a look at the key operating phases of AI pipeline. And then we'll bring in the carbon footprint characterization of AI model development, as well as the manufacturing footprints of AI system hardware. We will take a look at some of the recent studies that we perform on understanding the carbon footprints of large-scale machine learning tasks as well. Then the second part of my talk will focus on the wide solution space across the developmental phases of AI technologies and opportunities across the data center infrastructure and for on-device computing. Then I'll conclude the talk. So first, let's take a look at the entire AI model development cycles end to end. And this is an important step in order to have a deeper understanding about AI's environmental implications. Overall, there are 4 major steps in the AI model development cycle. We typically start with data, and then we extract important features from the data during the data processing phase. Significant feature engineering efforts is going into the steps. Then we move on to the second phase, which we call the experimentation phase. In this experimentation phase, we design, implement, and evaluate the quality of certain proposed machine learning algorithms, looking at new model architectures or training methods to determining model parameters. This model exploration process is quite computationally intensive, and very often a large collection of diverse machine learning ideas are being explored simultaneously. Once the machine learning solution is determined promising, we move into this training phase where the machine learning solution is evaluated using production data. And what I mean by production data is that this is data that's more recent. It is often much larger in quantity and contains much richer features as well. Finally, the best performing model is deployed for production use cases and is used to produce trillions of predictions daily in order to serve billions of users worldwide. Now, new data is curated constantly in order to fuel AI solutions for the next iteration, and this forms the virtuous development cycle for AI. At Meta, we see a rough power capacity breakdown of 10, 20 to 70% across experimentation, training, and inference phases. And at Meta, AI turns out to be the most data-intensive service at the data center fleet level. The amount of data used to train deep learning recommendation model, for example, has doubled over the past 2 years. And at the same time, because the training throughput has increases using training accelerators, we also see a dramatic increase in the data ingestion bandwidth demand. And in this case, within similar time frame, we see a 4 times increase in the data ingestion bandwidth demand. And this rise in data ingestion bandwidth is motivated the computer industry to actually redesign the data ingestion pipeline specifically for AI. And over the past decade, we also see that AI model sizes have been growing in conjunction with the increasing data volume. And these large capacity models have been shown to learn information a lot more effectively and in a more generalizable manner. So the figure here shows that over the past decade on the x-axis, the number of parameters of state-of-the-art deep learning models has been increasing exponentially. Natural language processing models such as GPT-3, Switch Transformer, or the recommendation ranking use cases stand out, especially from the perspective of their large model sizes. So we asked the question, like, what exactly is causing the model sizes to increase so rapidly? Taking deep learning recommendation model as an example, the model size increase primarily comes from using more embedding tables in order to learn information from the sparse features in the data set, and which is representative of new users coming online and some of the unseen items that we would like to learn information from. And in a study that we did between 2017 to 2020, the number of sparse features using these models have increased by 40 times. Furthermore, we are also seeing significantly larger embedding tables being deployed in order to capture the relationship between these sparse features and categories. And so because of this growth in the number of sparse features and the cardinality of categories per sparse features, it has driving the modern recommender systems into the terabyte scale already. And this is directly reflected in the amount of memory capacity required for processing these models. Now, the rise in AI data and model sizes translate directly into AI infrastructure capacity increase. And so for AI training, this means a 3 times increase in the AI server capacity over 18 months timeframe. And for inference, this corresponds to 2.5 times increase. Everything about AI has been increasing in a super linear rate as what we just seen across the dimensions of data, model sizes, and now system infrastructure capacity. Now, having seen the scaling trend of AI technologies, next we'll take a look at the power, energy, and carbon footprints of modern AI solutions. So we asked the question, how much energy does training a production scale machine learning task consume? So here in this recent work in sustainable AI, we look at 6 machine learning models that are representative of Meta's production task. We take a look at the large scale language translation model alongside with a wide collection of deep learning recommendation models as well. And this is what we found. Training a modern language model for Meta produces 45.2 metric tons of carbon emission. And just to put it into perspective, that is equivalent to 5 homes' energy use for a year, approximately. Whereas training a production scale deep learning recommendation models will produce carbon emission that's 9 times higher. And now once a model is trained, it is further optimized for production deployments. So here we are looking at the additional operational carbon footprints from the inference prediction phase of these machine learning workloads. Now, these carbon footprints is quite significant when we just look at model training. We also look at inference phases, and therefore to sustain these rising carbon footprints of AI, significant hardware software optimization effort have been devoted in order across the entire AI system stack. And so here, I'm going to take the universal language translation task as an example and share with you what kind of optimization that we will put in place in order to curtail the carbon footprint, the rising carbon footprints of AI technologies. So we would start with a CPU server baseline. And then we show that by performing application level memory optimization, we can improve the power efficiency by 6.7 times already. And what I mean by application level memory optimization, this is, for example, by caching frequently accessed embedding vectors for language translation tasks on fast memory. So for example, in this multi-level memory hierarchy, we can cache the frequently used embedding vectors on DRAM. or make the pre-computed embedding be shared across different application use cases. In addition to caching, we also deploy the language model across GPU-based AI hardware. This helps us unlock an additional 10 times power efficiency improvements. Furthermore, there's additional numeric optimization opportunities that we take advantage of by leveraging the low precision data types on the GPU accelerators. And finally, algorithm optimization provide an additional 5 times power footprint reduction. So overall, we can achieve over 800 times power footprint reduction through a combination of hardware, software, co-design, and optimization techniques. Such efficiency optimization is quite crucial, and it is a iterative process that we take in order to reduce the power footprints of large-scale machine learning tasks running at Meta's data center fleet. While these hardware software co-design process help us to achieve impressive power footprint reduction, for AI, the improved efficiency immediately translate into more uses. And this is also known as the Jevons paradox, where when the use case demand is high, efficiency improvements can encourage higher usage, and this will overall lead to even higher resource consumptions. And therefore, despite the fact that we achieve higher performance, power efficiency, the overall power footprint of the machine learning task continues to rise over time, in this case by 18% for the multilingual language model task. And so across these many different dimensions of AI, this growth trend easily outpaced the efficiency improvements at scale. And so despite the opportunities for optimizing energy efficiency and reducing the environmental footprints at scale, we must also take a look at how we can address the current scaling trend of AI beyond just efficiency optimization. Furthermore, on top of the energy and carbon footprints of AI training and inference, we must also take a look at the entire AI system lifecycle holistically. To do so, we use this lifecycle analysis or LCA methodology. So in this lifecycle analysis, there are 4 major phases from manufacturing, transport, product use, and recycling. So here we are going to focus on first the product use phase. This is the phase where the AI systems is used to perform all sort of computations, and the energy footprint of this AI computation translates into the operational carbon footprints. And here, operational carbon footprints means the carbon emission produced during the operational use phase of the AI system. In addition, we must also look at the embodied carbon footprint. This is the carbon emission produced when we build infrastructures specifically for AI. So this means like all the energy consumed when we start manufacturing, say the GPU accelerators, all the storage networking equipment in the AI super training clusters. So now having a peek at AI training's operational footprints a few minutes ago, you may be wondering what is the overall carbon footprint of AI and computing technologies in general? What is the breakdown between operational carbon footprints versus embodied carbon footprints? And that's what we are going to take a look next. So with colleagues from Meta and researchers from Arizona State and Harvard Universities, we analyzed the carbon footprints of computing in this work called Chasing Carbon. Chasing Carbon has been published at HPCA 2021 with a link at the bottom of this slide. So here in Chasing Carbon, we analyzed a large collection of publicly available sustainability report in order to understand the carbon footprint breakdown between operational and embodied factors. In this particular case, we analyzed Apple's sustainability report and find out that the manufacturing emissions dominates Apple's product. So here, hardware manufacturing accounts for 74% of Apple's overall emission. of which 33% comes from integrated circuits, such as the application processors, SoCs, DRAMs, and NAND flash. In comparison, operational use for Apple's devices accounts for only 19% of their overall emissions. So this is a story for client computing. For data centers, the manufacturing and operational carbon footprint is roughly an equal split. And I will refer you to the Chasing Carbon paper for further detail analysis. So while quantifying the exact environmental footprint of technology is a very complex process, and it is very challenging to be precise given the deep supply chain and the granularity of current measurement methodologies, we can already see how easily computing's carbon footprint can add up very quickly, right? And taking AI as an example, the overall carbon footprint is at least several times higher than that of model training. So now in the first part of my talk, we look back at technology development that has enabled significant growth for AI and for many different application use cases. We also look at the landscape of AI computings and their environmental footprints. Next, I'm going to talk about some of the directions that I think is quite important for our community to focus on going forward. What are some of the opportunities to scale AI research and product development in a more sustainable way, such that we can develop technologies responsibly and reduce AI's environmental footprint as much as we can. So look back in the past decade, we've been relying on this virtuous cycle of more computation power to process bigger and higher quality data to discover more powerful machine learning algorithms to drive up AI's prediction quality. We look at the environmental implications of AI computing is quite profound, and it is time for us and the entire computing industry, the research community, to focus the next decade on figuring out how to develop AI technologies in a more sustainable way. So what do we mean exactly by sustainable development? If we think about it, sustainability means that meeting the needs of present generation without compromising the ability for future generations to meet their needs. This is a quote directly coming from our Common Future, published by United Nations in 1987. And it resonated with me quite well when we were looking at sustainable development for computing infrastructures. And so first and foremost is for us to adopt a sustainability mindset when we are innovating in computing space. Specifically, there are several dimensions we must focus on. On the AI system development cycle front, we must focus on developing environmentally sustainable systems and computing infrastructure. On the AI training algorithm and model architecture front, we must invest in new techniques that balance the carbon footprint of AI by considering the unique breakdown of operational versus embodied carbon footprint. In addition, there are new optimization opportunities on the horizon for sustainable computing, for example, by exploiting the computer infrastructure at cloud scale and by achieving low carbon AI computing across the entire computing spectrum between cloud and the edge. So while my talk focuses on AI, many of these design principles are fundamental across computing technologies. So think about how this relates to your work and the impact that you may be able to bring onto the table. Now, after seeing the carbon bottleneck of computing to shift from product use phases to system hardware manufacturing, the first dimension that I would like to bring to your attention is how to develop environmentally sustainable systems going forward. As a computer architect, I see two low-hanging fruits. First is the role of virtualization for AI accelerators, okay? So what I mean by that is that to amortize the upfront embodied carbon cost, we must maximize utilization for systems already deployed. And I'm going to take GPU as an example for AI accelerators. So here I'm showing the GPU utilization for supporting a large collection of machine learning experiments that we run on our training clusters. On the x-axis are the various GPU utilization levels, whereas and this is a histogram that shows the number of training jobs and their respective utilization level. So what we see is that despite the fact that these machine learning models should run quite well on the GPU accelerators that's developed specifically for training, there's a large collection of experiments that is actually utilizing GPUs only at 30 to 50% utilization level. And this is an opportunity for us. By increasing these GPU utilizations, we can expect that the embodied carbon cost can be further amortized. And what it means is that for model developers, developing model architectures that can better utilize accelerator resources more efficiently can help improve amortization of embodied carbon cost. Furthermore, multi-tenancy execution on these AI accelerators can also help. Second is to prolong system hardware lifetime as much as possible. So now, when we start extending system hardware lifetime to amortize the upfront embodied carbon cost, we will start observing the failure rates of various system hardware components to start increasing over time. This is because of all the wear out effects on the hardware components. Some of these hardware failures can be mitigated with hardware redundancy or using mechanisms like ECCs, for example. However, some of these errors can also be masked through new software solutions. And therefore, what I see as a new opportunity is for software architects to develop software system architectures for aging hardware. By extending the lifetime of these systems, that's a really good way to amortize the manufacturing footprints of systems in general. Furthermore, if we think more about the failure characteristics of the different system components, they can be quite unique. And therefore, when we develop new system going forward, keeping modularity in mind could be quite powerful in order to reduce the overall environmental footprints of computing. That's a little bit about the data center. Now, if we look at consumer electronics, we see a similar significant shift of carbon bottleneck from operational to embodied carbon. So here, to illustrate the significance of the shift, we analyzed 2 generations of iPhones by taking iPhone 3 from release from year 2009 and iPhone 11 released a decade later. What we found is that during this decade, iPhones are seeing about 1.6 times reduction in its operational carbon footprints, while the manufacturing carbon footprint has increased by 3 times due to more advanced hardware architectures that leads to much higher hardware manufacturing cost. And the reason why we are seeing this trend is primarily because there is a strong user demand of low latency, low power, and low energy consumption at the product use phase. However, this operational efficiency gain comes with this upfront embodied carbon cost. And for example, the more domain-specific accelerators, specialized hardware that we incorporated into the newer generations of consumer electronics, that is going to bring in additional embodied carbon cost. And without doubt, AI is driving the design of mobile processors in the consumer market. For example, Apple's A14 Bionic accelerators already devoted 25% of its die area for neural engine. Similarly, for the M1 processors, significant amount of die area is devoted to AI processors and other programmable accelerators as well. So now the exact carbon optimal operating point is going to vary, and that depends on the use cases that we develop hardware for. However, as a system hardware architects, what is important to keep in mind is the balance between operational performance energy efficiency, the utilization of the silicon, and therefore the embodied carbon cost that goes into it. And in this case, knowing your workloads and use cases for what system hardware that you're designing for is super important. Next, I want to touch upon what kind of opportunities that AI algorithms, model architecture dimensions can help reduce the environmental footprints. So as what I showed earlier in my talk, the memory capacity requirements of industry scale machine learning tasks is growing exponentially. And the memory capacity demand is already moving into terabyte scale for production use cases. So in this recent work that we published at MLSys 2021, we asked the question of, can we design model architecture to learn all the necessary information from data while being significantly more memory efficient? So while the original motivation of this recent work called tensor train compression or TT-REC was not meant for minimizing AI's carbon footprint, it is quite an interesting example that shows how model architecture can be designed in order to balance an algorithm static memory demand with runtime computation. In TT-REC, we proposed replacing the large embedding tables with a sequence of low-rank matrix multiplication. And by doing so, we are trading off the memory storage requirements with recomputation. So this is quite analogous to how we can reduce embodied carbon footprint by trading off operational carbon footprints. In this work, we show that TT-REC can achieve 2 orders of magnitude memory footprint reduction while experiencing only 10 to 20% training time overhead. In this particular technique, we highlight that TT-REC presents this interesting design space trade-off between memory capacity, training time, and model accuracy. And we also expect that the lower embodied carbon footprint can be achieved through TT-REC because it is requiring much less on-chip memory capacity, whereas the operational carbon footprints can be further optimized away with additional architectural level memory optimization or with the use of renewable energy that's available in most of the public cloud providers. Yeah. Moving on to what optimization opportunities that we have at scale. So to achieve net zero, we've looked at how Facebook Meta has invested in renewable energy infrastructures and power grids where data centers are located exactly. And so here is a US map where we show where Meta's data centers are located and where the renewable energy investments take place as well. And this is a great move because cloud users today can benefit from economies of scale by running their computations at hyperscale data centers where carbon-free energy is available. However, depending on the specific approaches, there can still be varying degree of carbon emissions from data center computing because renewable energy generation is intermittent in nature. For example, depending on the delay tolerance nature of workloads, computations may be shifted to time of the day when renewable energy becomes available, or to data centers at different geographic locations where renewable energy is more plenty. So here, globally optimal solutions will require a holistic perspective. And we also must consider both operational and embodied carbon footprint, where this additional embodied carbon footprints can come from energy storage in order to smooth out the intermittent nature of renewable generation, or having to incorporate additional server capacities in order to accommodate computation shifting opportunities. Furthermore, our current software stack assumes stable power sources And now thinking about renewable energy availabilities that can vary quite a bit over time. An interesting research direction that our communities should start looking into is to explore and design the next generation software system stack in order to support computations with intermittent energy sources. There is some work already going on for client computing space. Some more can be done for cloud scale infrastructures as well. Going forward, while we see a significant portion of AI happens in data centers today, a lot of learning AI computations is starting to shift for on-device in order to improve data privacies. So next, I'm going to talk about what kind of AI happens at the edge and what kind of opportunities that we should think about. What are the unique challenges that we face when we start developing computations between the entire computing spectrum, connecting the data center infrastructures all the way to edge computing. Now, if we think about renewable energy availabilities at the cloud scale, it is actually lots of work is going on, and that has made the availabilities to become quite prevalent. However, if you look at the access to renewable energy for edge computing, it is far more limited. And given more computations are happening at the edge, there is additional carbon footprints that will increase for computations happening at consumer electronics space. So in this study that we did recently, we found that on-device learning, such as federated learning use cases, can incur quite a bit of carbon footprints. And in many cases, that can be several times higher than some of the large model training in the cloud setting, while considering availability of renewable energy especially. So now when we consider the scale and the wide variety of on-device AI use cases, such as the smart home gadget, AI happening at laptop, smart wearables, the carbon footprints can add up very quickly to a significant amount. So what this means is that low carbon energy efficient solutions is needed more than ever for the edge space. Solutions must guarantee user experience and high prediction accuracy. At the same time, we also want to reduce the carbon footprint as much as we can. However, making on-device AI efficient and viable is very challenging. It's going to require software developers and system architects to deal with the highly fragmented mobile ecosystem, the highly dynamic environmental factors, all sort of network stabilities and interference phenomena on user device. And furthermore, making solutions to work at scale is quite complex. And so here I see many new application domains to emerge at the edge. There's a strong use case demand. And what that means is that it would also expose new opportunities for optimization across the entire system stack in order to sustain the market growth and while being environmentally sustainable for AI and computing technologies overall. So having seen some of the future directions that I see happening in sustainable AI scaling, I will next conclude my talk by looking at what happens in the past 50 years. We have seen impressive technology advances that has bootstrapped the AI revolution. We have focused the past decade on operational performance and energy efficiency optimization. And today we see significant environmental implications of AI computing. So what should the community focus the research and product development efforts on in order to achieve a sustainable future for computing going forward? If you remember, the title of my keynote is to scale AI computing sustainably, where AI is the most critical application driver that has seen this superlinear growth across many dimensions, including data, model sizes, infrastructure capacity requirements. Now, in order to focus our energy on the most important piece of the pie, we must look at the AI development cycles end to end, including data storage, ingestions, experimentation and training, and model development. All three dimensions contribute significant energy footprints for AI solutions, and therefore, a lot of efficiency optimization should happen in order to reduce the carbon footprints of these development phases. We must take a holistic approach when quantifying and optimizing for AI's environmental footprints, not only by including operational carbon costs, but also think about the implications of embodied carbon costs as well. This is where we get to make real world impact in the case fighting climate changes with computing technologies. However, this is not going to be an easy process. Characterizing and analyzing carbon emission is a complex process as compared to what we are familiar with for performance measurements, power and energy modeling for computing systems. So while there is some initial efforts, for example, the MLPerf benchmark suite has already proposed a standard way to measure power consumptions of AI systems, there isn't a standard metrics or mature tooling available yet to standardize carbon footprint measurements, not to even mention environmental footprint measurements for computing holistically. And this is what where I want to challenge our communities to take part of. And today I'm really excited to also share two recent tools that we open sourced in order to help advance the tooling space a step further. One is called ACT. This is the architectural carbon cost modeling tool that we developed in order to enable system hardware architects to develop sustainable AI systems or systems in general. And on top of that, we also open source Carbon Explorer, a tool that helps system infrastructure developers to look at how to design carbon-free data centers by taking into account renewable energy availabilities, by taking into account energy storage, as well as computation requirements at data center level. And to scale the growth of AI technology sustainably, we also need frameworks to enable us to put environmental sustainability as the first-class design principles when architecting next-generation system architectures. And so here I see plenty of exciting opportunities across the entire system stack, from programming language, how do we encode, for example, delay tolerance of computations into workloads? How do we implement that to exploit the delay tolerance nature of workloads for computation shifting, for example? That's going to require new runtime management solutions. How do we develop system architectures, optimize hardware design by reducing the carbon cost that goes into computing hardware, while also be able to fulfill the performance requirements, the power efficiency requirements at the same time? Finally, to support the growth of AI technologies, we have to innovate sustainably, develop and deploy technologies in an environmentally responsible manner. So while enabling more sustainable scaling for AI, there are also plenty of opportunities to deploy AI technologies to tackle climate change challenges as well. So I see there's a lot of synergy between AI and environmental sustainabilities, using computing technologies to solve climate change challenge and vice versa. This is where I would like our community to take on, and hopefully this is going to be very rewarding directions going forward. So a significant portion of my keynote today is based on this position paper that we put out, where you can find a lot more elaborated analysis on various aspects that I talk about today. In addition, with colleagues from Google, Microsoft, and Harvard, we also share some of our thoughts on the socio-technological challenges for digital technologies. And finally, I would like to share some pointers to recent work that we have in the space. And the work I get to share with you is carried out with many students colleagues at Meta and colleagues at academia. So I would like to acknowledge and thank all our collaborators and everyone's contribution to the work that I get to share with you. It wouldn't happen without all the collaboration that we have to move the needle forward. So thanks so much for your time and attention. And I would really love your inputs and your thoughts on how to move our computing infrastructures into a more sustainable way. Thank you.
Thank you, Carole, so much. And I think it's worth a round of applause virtually as well as physically in the hubs. Thank you so much. There are already quite a number of questions in the Slack channel. I'm sure we can generate much more in the limited amount of time that we have. I would like to address the first one. The first one is actually covering or targeting that superlinear growth that you presented a couple of times here on your slides, which is kind of discouraging. So the first question would be, do you see an end to this? I mean, are there any saturating factors that might play a role for this effect coming to an end, even considering Jevons paradox that you mentioned, which actually means that opportunity increases growth and so on and so forth. And on a second note, Noman Bashir from the Amherst Hub cited David Patterson from Google with his paper titled "Carbon Footprint of Machine Learning Training Will Plateau Then Shrink." So that's basically also opening up a different perspective. So what is your thought on this?
Yep, great question. So the first part is on the superlinear growth of AI. So if we look at just in general, energy footprints of anything, it is reflective of actual economic growth. And so if we, it's going to be very hard to predict the future. I guess that's what I'll put up front. But if we expect the AI space to grow in the next decade, it is going to come with energy footprint implications. And so to me, what that means is that as a technology developer, what we need to keep in mind is that we should not just like chase after that 0.001% accuracy improvements while not thinking about all the computation resources or the environmental footprint that may sort of come with that particular, sometimes insignificant accuracy improvement, right? And so sort of keeping that in mind is quite important. And now I see several optimization opportunities here is that we should look at how to develop AI algorithms such that it is a lot more resource efficient. If we think about the past decades, we've been working on innovating in the model architecture space and just let data volume to grow. There is actually a lot more that can be done by learning how to utilize these AI data more efficiently. And that also is a really good way, underexplored area to reduce the energy footprint, environmental footprints of AI technologies. And on top of that, I think we should also think about where AI technologies can help to reduce, for example, in the beginning of my talk, I talk about how AI can help discover new electrocatalysts for next generation energy storage materials. That is a really good way to utilize AI to solve climate change challenge. On top of that, agriculture industry is contributing to significant carbon footprints. And so how do we use AI technologies to improve the efficiency of agriculture and to improve actually just various different operational efficiencies for different industry sectors? Those are some of the things to keep in mind as well. To the second part of the question, Dave Patterson et al. From Google has talked about how AI computing's footprint is going to plateau in the next decade. I hope that that's what we see. That I think that's a prediction for what's going to happen in the next 10 years. And in order for us to get there, there is actually a lot of work that needs to be done. Not only that, renewable energy utilization needs to improve. There is a lot that we can help on model development front, as what I said. Let's figure out how to bend the growth curve of AI such that we can achieve higher model accuracy by using much less computation resources. And that's implications on both operational energy footprint as well as embodied carbon footprint, right? Like, how do we move the field of AI without requiring thousands of GPUs, or sometimes even more, when we start looking at large scale machine learning models.
Thank you so much also for the very inspiring answer to the second part of the question. One follow-up question. You mentioned the more efficient use of data. As now e-energy is also focused on AI applications, one observation could be that, well, we do a lot of redundant training here. So of course we get our hands on powerful machine learning hardware, the data sets. But then again, all the research groups redo the, I would say, basic training again. So training on not the same, but similar data sets. So isn't there also the responsible or our responsibility to share trained networks at some quality assured level, documented, fair and open, but really before we start training again, look for a reusable network that we transfer learning can reuse for our needs?
Yeah, really great point. This is something that I'm seeing a lot more awareness by the machine learning community for sure. And as an opportunity, I would like to give a shout out to my Meta colleagues. I think most recently we open source this pre-trained language model called OPT. And this is exactly how we can help advance the field by, open sourcing, making large-scale machine learning models available, the pre-trained model available, and that's going to help sort of amortize the upfront training costs for things that doesn't need to be redone.
Maybe a quick question. Sonja Klingert asks, what is the share of workload at Meta that could be shifted in time? I mean, you presented that flexibilizing parts of that to times where you have more renewable energies could be one perspective. Can you give a percentage on the flexibility that you have at Meta?
Yep. In our recent work, Carbon Explorer, and we also have a position paper to be presented at Hard Carbon Workshop called Carbon Dependencies of Data Center Computing. Over there, we talk about how about 25% of workloads at Meta is flexible. And I think Google has also shared their number, and that's about 40%. And maybe, of course, like a lot more detail is in the paper, which I encourage you to take a look at.
Yeah, that would be great. So we could share it and distribute it. Maybe one additional thought is also to use the excess heat from the special purpose computing to do something. We have a great project here, heating a public swimming pool, so swimming stadium with the excess heat over a high performance cluster. So that works. Maybe one final question. Could be the question to end all questions by Dan Wang. What's the implication of our world moving into metaverse on carbon emission?
Oh, yes, this is the time to start looking at that. I think one of my sort of favorite quote is by Peter Drucker is to measure is to optimize. And so, I mean, intuitively, metaverse is going to require tons of computing infrastructure to support. And intuitively, for like all of us technology developers, the energy footprint of computing infrastructure that supports metaverse is going to be significant. So I think this is time that we think really hard about how to move ahead such that if we are going to develop and design this computing infrastructure from scratch for applications such as metaverse. What do we need to do actually? And we now have some of the tools available in the space. We can use ACT to quantify the carbon footprint, embodied carbon footprints of system hardware developments that can help system designers to look at what kind of computing infrastructures that we can develop in order to lower the carbon footprints of some of these computing infrastructures that we're going to build between edge data center to cloud. We should think about, I think this is just so exciting that it is an opportunity for us to reinvent the entire system stack, all the way from software programming language down to system hardware development. And so I encourage and want to see all the novel ideas that our community can come up with, such that we can actually build a sustainable metaverse without gobble up all the energy resources that we have on this earth.
I'm positive that we can and will solicit some papers on the topic for next year's and future e-energy conferences. That brings us to the end of today's keynote presentation. Carole, thank you so much for the great keynote, for the great discussion, everyone else for participating in that discussion. Yeah, we will make the keynote available sometime after the conference, when we slept enough to be on top again after the conference, via our YouTube channel. And yeah, Carole, have a great day. Good luck and success with all your work. And yeah, we are now continuing the conference. Thank you so much.
Thanks so much, Sebastian, and everyone.
Yeah, and with that, I think another round of applause is a good idea. Yeah, and with that, we continue now in the European Mirror with session 6. So everyone, please change who was in the European Mirror and plans to stay there and resync to the European Mirror again. I think we will start maybe 5 minutes late. And yeah, everyone else in the North American Mirror, have a great day. And yeah, have an exciting session 4. We already know what's waiting you and coming up, but no spoilers at this time. David, Norman, have a great day. See you later.